Okay, next we're going to talk about waves and sound for a few minutes. Okay, so with this one, we're going to look at period, frequency, wavelength, some parts of waves, and Doppler effect. So actually, we're going to start with Doppler. So here we've got a person standing here on the side of the road, and there's a fire truck going by. Okay. So, what's the best description of the pitch and frequency heard by the observer as the fire truck moves away from them? So, with Doppler effect, you've got sound waves that are either they're coming at you and they're compressed, they're like smushed together. Okay, so you're going to hear a higher frequency sound. Okay, the sound is the same, whether it's coming towards you, going past you, going away from you. But this is a perceived, if I could spell PERCEIVED, a perceived frequency by the observer. So you, the observer, hear a higher frequency sound as something's coming towards you. Okay. So here's our fire truck coming towards him. And that means the pitch is also going to be higher. Remember, pitch is how we hear sounds and it correlates to frequency. And that's because these sound waves are compressed. Okay. And then as it's going away, which is really what's in this drawing, the sound waves are going to be spread farther apart. So our perceived frequency and thus our pitch are going to be lower. Okay. So let's see if that's one of the choices. Hopefully it is. Let's see. As the fire truck drives away, higher pitch. We're looking for one with lower pitch. The observer hears a lower pitch because the wave compressions reach ears with a higher frequency. No. Lower pitch, lower frequency. So it's going to be D. So those sound waves are like crunched together, is kind of the way I think of it, as the sound is coming towards you. That's why you hear a higher pitch, you perceive a higher frequency. And then as it moves away from you, they spread back out. So you get a lower pitch and a lower frequency. Again, the fire truck is making the same sound the whole time. It's just the way we, the observer, perceive it, the way our ears process those sound waves coming in. Okay. Okay, so how does the energy of the mechanical waves above compare? Okay, so these are mechanical waves. That means they're moving through some kind of medium. And with mechanical waves, we looked at energy as connected to amplitude. Okay, amplitude is our max distance from our like our zero line, our equilibrium line. Okay, so in the case of these two waves, it looks to me like their amplitudes are the same. Like this looks like the same height from this line to this peak here. So that would be this as this. And I don't have a ruler handy. Okay, but I feel like they look like they're pretty close enough to say that they have the same energy. Okay. So with mechanical waves, we look at the amplitude as giving us information about it, energy. Sound waves are represented by a device that shows them as waveforms. So these are different notes. Which note has the highest pitch? So we just talked about this a moment ago, where pitch is connected to frequency. Okay, they're kind of direct. So if you have a higher frequency sound wave, you're going to hear a higher pitch sound. Okay. And so if I look at these four waveforms, it looks like this one has the highest frequency. Remember, frequency is our number of cycles per time, or wave forms over a given time. So if all these are the same time, this one, I mean, I see 1, 2, 3, 4 complete waveforms here versus two, and really just one here that's got kind of a longer wavelength. So I'm going to say C is going to give us the highest pitch because it's got the highest frequency. So these two have a direct relationship. Okay, so then we've got a wave here traveling through a string. What is its speed? Okay, so speed of waves, we calculated that using frequency times wavelength. Frequency, I just talked about that being our number of cycles per time. And then wavelength is like a length. It's like a distance of our one full waveform. Okay, so I could measure wavelength by looking from the beginning here to the end. I could also do it from a peak to a peak or a valley to a valley. In any case, I need one full waveform for a wavelength. Okay, so wavelength is the length of one full wave form. So it's got to be a full waveform, not part of one, not 3/4 of one, a full waveform. So if I look at this is kind of small, but I can see that it looks like this is 8 centimeters, okay, for my wavelength. And they give me frequency, which is 60 hertz, okay. So I'm just going to take 8 centimeters and multiply by 60 hertz. That should give me 480 centimeters per second. And again, let's see, I think I cleaned up this formatting in case anybody wants this printed out. So it's not on multiple pages like this, but there's 480 centimeters. Yay. Okay. Okay, a couple more. 2 students shaking a slinky, making a wave. How can they change the speed of the wave? Okay, this one was kind of tricky. This is similar to one we had on the test for this unit, but with waves, with mechanical waves, okay, they are in a medium. They're in some kind of material. It might be air, might be water, might be some other liquid, could be a solid, who knows. But because of this relationship, okay, if you change one of these, the other one is going to change correspondingly. These two have an inverse relationship. So you can't change the speed of the wave by changing one of these for the wave. Like if you increase the frequency of the wave, you're going to decrease the wavelength, okay, or vice versa. The way you have to change the speed is to put the wave in a different medium. And then when you do that, that's actually going to change its wavelength because now it's in a different material. So move the slinky to a pool of water and shake it there would be the answer here. Remember, amplitude has to do with energy, okay, not any of these things. And again, if we change frequency or we change wavelength, all we're doing is changing the other one. Okay. So that can be a little confusing. That applies to mechanical waves. Okay, so mechanical waves, they require a medium. So a solid, a liquid, or a gas, you've got to have one of those for a mechanical wave to travel through. Okay. All right, the last question has to do with this standing wave. Remember we talked about standing waves. We talked a little bit about like music. We made notes with those palm pipes, and we talked about how a standing wave, it's really a pattern of wave interference that goes, it's waves that are reflecting back and forth. They form this pattern where they look like they're standing still. Pattern of interference. Okay, So for the standing wave above, all right, so A, this is labeled A, this is called an antinode. And this is a point of maximum energy where basically my two amplitudes of my waves have combined. So I've got the biggest amplitude here. And then B, these little points called B here, that's called a node, and that's a minimum energy. So that's like the opposite. That's like where my amplitudes have canceled out. So when I've got these two waves reflecting and forming this pattern, in some portions, their amplitudes are going to combine so that they've got one bigger amplitude. In other cases, their amplitudes are going to cancel out. And we also talked about this as constructive interference, where our waves combine, and destructive, where they cancel out. So this is just another example of that. So, okay, so that's going back through waves and sound.